I'm going to talk a bit about this computation approach, approximate Bayesian computation, that's originated in recent years in population genetics, although I believe there are examples of its use many years ago. But it has mainly been used until now in population genetics problems. And I think, as I'll discuss later, population genetics may not be the main home for ABC because there are other competing methods, but there are other sorts of problems that we might want to apply it to. This talk is mainly going to be describing, it's mainly a review of ABC methodology and a discussion of some of the problems, the current problems and current work. And then I'm going to talk a bit about some recent work that I've been involved with, which is to try and extend the range of application of the ABC approach to cases where there are very many parameters and such as hierarchical models. And so I'll talk a bit about that, or quite extensively about that in the last half of the talk. And then I'll give some tentative conclusions and outlines. Forgive me if you know it all already, but the first half of this talk is really going to be trying to get us up to speed about what the ABC method is and how it originated. So it's a Monte Carlo method that's proved useful for analyzing complex models in which the likelihood function is difficult to obtain. And the key feature, or key features of the method are that you don't require the likelihood function to be specified beforehand, because there are many problems in which it's very difficult to actually write down what the likelihood would be, but we can simulate from them relatively easily. So there's always this problem in that it's quite easy to simulate data sets, but the inverse problem is generally very difficult. It's difficult to simulate parameters that could have given rise to a particular data set. And the method is typically based on summary statistics that are computed from the data, and the accuracy of the method will depend on the level of sufficiency of these statistics. And it's an easy framework for model choice problems, although I'll only talk about those problems obliquely in this talk. Here's a brief recent history. Simon tells me that there are earlier papers that have used the method, but I think the story for many of us in population genetics starts with a paper by Pasaran and colleagues, including David Balding and Peter Donnelly, who suggested the use of a rejection algorithm to infer demographic parameters in population genetic models. Okay. So for a lot of population genetics problems, you can, given some genetic data, it's quite easy to set up a model in which the demographic history of the population can affect the data. And so given some data, what you're interested in doing is trying to recover the demographic history. And that's been a motivating concern in population genetics, particularly for the last 15 years or so. And these sorts of problems are just on the cusp of being tractable in population genetics. And I think that's possibly why it's an area in which the ABC method has flourished, because it's not such a total black box. There are real problems where you can get solutions by other methods, by Markov chain Monte Carlo methods or importance sampling, and then you can compare the results that you get with the ABC method. And the consequence has been that there's been a level of certainty in the conclusions that have been drawn from the ABC method, because we can apply MCMC to simpler problems and it works okay. And then the idea is that you'll apply the ABC to a more complicated problem and fingers crossed it's giving you a reasonable answer. And the first paper which really developed an ABC, a recognizable ABC approach, would be the paper by Pritchard et al. In Molecular Biology and Evolution, where they introduced a particular algorithm that I'll talk about in the next few slides. And from then on, a series of papers developed looking at the problem from different points of view. And recently, there seems to have been quite a flourishing set of papers in statistical journals that are looking at these ABC problems. So there are three flavors of ABC that are current. There's the view that was impressed upon me by Wenyang Zhang when he was working with me and David Balding, that you can view the problem as a conditional density estimation problem. And I'll begin by talking about ABC by introducing that aspect. And then another approach has been to use Markov chain Monte Carlo methods, which are potentially more efficient, and then sequential Monte Carlo methods that are potentially more efficient still. So if we just think of it as a regression problem, we've got the joint distribution of the model parameter and the data, or a summary statistic computed from the data. And in the so in the Bayesian world, you set this up by simulating from the PRA, and then using the method composition, you then simulate from the likelihood function. You end up with this joint distribution. And we've observed some data, let's call it Y, and we want to get an estimate of the conditional density at this point. And so that really is Bayes in a nutshell. And if you look at it like that, then all that we are interested in doing is some form of conditional density estimation. But you can see that there's a problem here in that typically, if the data are telling us something about the problem, then the posterior distribution should be much more peaked compared to the PRA. And so this general approach, this naive approach, if you like, of first simulating from the prior and then from the likelihood and then computing this conditional density is quite inefficient, which is why the MCMC methods and the sequential methods have been developed. But nonetheless, I'll just carry on talking about conditional density estimation to begin with. Because even though you have this potential inefficiency of sampling from the prior, if you can use the information about the full joint distribution to make a good estimate of the conditional density there, then maybe this inefficiency doesn't matter. And it's so I'll discuss that a bit later on. So in the approach that was taken in Beaumont, Zhang, and Balding in 2002 was that we measure some summary statistics from the data, and we simulate n random draws from the prior and compute the summary statistics, and then, incidentally, these are scaled. And we assume that locally, within this little region here, we have a linear model, and this parameter alpha, this is the posterior mean that we're trying to estimate. And so we use least squares, and we try to estimate alpha, which is, gives us the posterior mean. And we, in the approach that we took, we used an Epenichnikov kernel. So that means that data or summary statistics that are measured at a greater distance than epsilon from the observed summary statistics have a weight 0, and then otherwise they have a quadratically increasing weight up until the actual observed value. And we made the assumption that the distribution of the errors is constant within this region. Sorry, this should be rho here. This region here. And we then adjust the parameters just simply by scaling the residuals to be residuals as if they were from the distribution at the observed point. And this algorithm seems to perform quite well. So if we compare with the original method of Pritchard et al., you find that the relative mean square error typically increases rapidly with the tolerance, whereas the regression method is less affected by the tolerance width. And in this particular example, which is a genetic example, I don't want to go into it in any great detail, you get these sorts of pictures, whatever problem that you're looking at. But in this particular problem, which is a complicated genetic problem, there was an MCMC solution, and this is the mean square error that we got using the MCMC method over 100 or so independent simulations. And so you can see that the ABC methods and the MCMC are competitive, although typically they're not as good. So, yes, the other point of this slide is that to say that the Pritchard et al. Method is one essentially where you accept just all the points within this window and without any adjustment, and that is why you get this increased mean square error. So the basic regression approach has been further improved by Blum and Francois, and in two ways. First, they relax the assumption that the distribution of errors is constant within the interval by performing an extra regression on the residuals, and so you can adjust for heteroscedasticity. And secondly, rather than using this local linear approach, they used a non-linear regression based on neural networks. And they were again able to show using these mean square error type plots or integrated square error, that again you get an additional and occasionally quite substantial further improvement on the original linear approach. So a Monte Carlo approach was then proposed by Marjoram et al., which is potentially much more efficient because you're not sampling from the prior. And so essentially you simulate a new value of theta from your transition kernel, and then you simulate from your likelihood function a data set, and if it's within some interval, then the new value of theta will be your proposed value, provided the usual Metropolis-Hastings calculation holds, okay? And certainly in the case, if you had, for example, discrete data, and these weren't summary statistics, rho, x, and y, and you match them exactly, then you can show that this approach will satisfy detailed balance, and this would give you a correct simulation from the posterior distribution. And in fact, you can generalize this a little bit more because you can see that this is, if you like, Monte Carlo sample of size 1 from the likelihood function. And so just by increasing the number of times you compute this, you'll get an estimate of the likelihood. And as Gareth will show in the next talk, you can still show that you satisfy detailed balance with that sort of an algorithm. And that has actually been used as a way of improving on the Marjoram et al. Approach, and I'll discuss that a bit later on. I'll discuss that in this slide. But, now this MCMC scheme has been very widely used, both in and out of population genetics. And quite a nice example, I think, is this paper by Beckett and Przowski, where they looked at, again, a complicated model. This is a model of populations that are diverging over time from a common ancestor. It's a genetic model. There's gene frequency differences arise, and you're trying to use that information to say something about the time that the populations have diverged and the population sizes of those populations. And again, this is a problem where there's an MCMC alternative, but it rapidly gets problematic when you have very, very many loci. And so an ABC method is indicated because you can compare, as they did, the ABC method with the MCMC method for a small number of loci and show that it works really pretty well. And then in the cases where the MCMC won't work, with a large number of loci, you're making the assumption that the posterior distributions are reasonable. In their approach, as I think I discussed in the next slide, they used this Monte Carlo trick to improve on the performance of the MCMC scheme. And a couple of papers by Oliver Ratman have, and colleagues, co-workers, have used this MC-ABC scheme to look at models of to infer parameters in models of the development of protein interaction networks. And this paper by Bortot et al. In JASA again used the MCMC-ABC to look at a metallurgical problem with some success. And there are others. These are the ones that I find particularly interesting for reasons I'll go into the next slide. One of the main features or problems, depending on how you look at it, of the MCMC-ABC method is that the rejection rate is, the acceptance rate decreases in the tails. And that's not really desirable, because if you're out of the tails of the distribution, then you'll tend to stick there. So it tends to make the MCMC very sticky. And so people have addressed this in a number of ways. So I won't go yet again about the Beckett and Brzozowski method, but they increase they make an improvement, if you like, in the estimate of the likelihood from just a single sample. Then another approach is to have a sort of tempering approach. So you make sure that your starting point is well within the posterior distribution to try and minimize excursions to the tails. And so you could do that by having a very wide tolerance in the early part of the MCMC. And then as you progress, you decrease the tolerance until you get to a certain limit, and then you stop at that point and then run the MCMC. Obviously, you can't keep changing the tolerance because you wouldn't keep detailed balance. Or you couldn't keep changing the tolerance systematically. You can, however, validly augment the MCMC with this tolerance value, this epsilon, and then look at your parameters marginal to the tolerance. And this produces a much more relaxed MCMC. And if you wanted to, you could condition the chain on very low tolerances, for example, and get a good estimate of the posterior distribution. And so this, in a way, seems to solve a lot of the problems. It does produce additional features that I'm not actually going to talk about, but they are quite interesting in terms of the accuracy of the ABC when the summary statistics that you observe are not well within the prior predictive distribution. So if you just sort of go back, I'll go back a few slides to this picture again. So I call this the marginal likelihood, but another way of looking at it is it's the prior predictive distribution of your summary statistic okay, because you've simulated from the prior, you've simulated from your model. And if your data are a long way out, in the normal course of events, you can still validly compute a likelihood and a posterior distribution and so on. But in the ABC world, you can't do that very easily. And, well, you can still get an answer, but what does that answer mean? And that is an open question that is something that we'd maybe like to talk about later on. Okay. So then a sequential, motivated by the problems of the stickiness and so on of the ABC and SMC, a sequential Monte Carlo sampler was introduced, which extended the approach of Del Moral, Doucet, and others. How much longer have I got? Because you started about 10 minutes late. 15. So this was explicitly based on the approach to sequential Monte Carlo of Del Moral, Doucet, and Jazra. And there have been a set of subsequent papers that have been strongly motivated by this Sisson paper. And one thing that we've noticed, that has been noticed, is that there's a bias that's in the original algorithm of Sisson et al. And this bias originates because the results in Del Moral, Doucet, and Jazra don't automatically translate over into the ABC world. And again, I'm not going to go into that in any great detail, but this bias has been recognized in recent correction by Sisson et al. And is discussed in some detail in this paper with Christian Robert and Jean-Marie Cornier and Michel Marin and Biometrica. So the scheme, there are a number of different schemes. They're all quite similar, and so I'll just talk about the scheme that we worked on, which is, so you define, and in many ways this follows quite closely the original Sisson et al. Method. So we define a sequence of thresholds, and in the first iteration, we simulate n particles from the prior, and then we simulate data from the likelihood and conditioning on the data being less than our first tolerance, epsilon. And we set our initial weights to be uniform. And then in the second iteration, and subsequent iterations, we pick the new thetas from the old thetas in proportion to their weights, and generate new values of theta from these that are sampled from their weights with a little bit of noise. So we have a kernel, a smoothing kernel. And so one way of looking at this is that essentially we're repeating the same procedure as the rejection method, but we have a different sampling distribution each time. So in the original rejection method, we sampled from the prior, but now what we do is we sample from a new distribution, And we just have to correct for the fact that we're sampling from this new distribution by giving it an importance weight, which is the prior over your sampling kernel density. And so that is done here. We set a new weight, and then we repeat this procedure. And so here's an example of the method being applied to a toy problem. So we sample theta from the prior, and we have a target problem, which is a mixture of two normals, a low and high variance, and our observation is 0, and we have 1,000 particles, and then we successively decrease the tolerance. And these plots show in the dotted line is the actual true posterior distribution. In the black line is the posterior distribution that's attainable within the error bound. Okay, and then the coloured points are simulated points. And so you can see that as you decrease the tolerance, you increase your you increasingly match the target. Now you can actually improve further the sequential method. So here's some results again in one of these complicated population genetics problems where you have a population that's diverging into two populations, and you're trying to estimate some quantity. In this particular case, everything is fixed. So the data was simulated with certain parameter values, and those values were used as point priors apart from the one that we were interested in. And in this, you can see the improvement in the mean square error that you get from the sequential method plus regression. And what is particularly interesting is that which is a feature of the regression approach, is that the error is still really quite small, even in the first rounds of the iterations in comparison with the pure sequential method. Okay, so I'll try and speed through this. So I'd like to just talk a little bit about some recent work that we've been doing on hierarchical models in ABC. So these models pose a problem because there are a large number of summary statistics which grows with the number of exchangeable units, or the replicates at the sort of lower level of the hierarchy. And there are a number of examples in population genetics, so modeling variability and mutation rate, looking for selection. And the problem we're going to be talking about is a problem of looking for selection at genetic loci, and modeling assignment of individuals to populations. In all these cases, the number of summary statistics potentially you have to compute scales with the number of individuals or number of loci that you're working with. So in this, for this particular example, we'll just change the notation slightly. So we have the hyperparameter alpha, and then we have the data that's observed at a particular unit is x, and then kappa and lambda are parameter vectors. We made the distinction between kappa and lambda for some obscure reasons. You can think of them as being interchangeable. I think the original idea was that some were observed and others. Kappa is a nuisance parameter, like a genealogy. It's just part of the model, if you like. And then we denote by x0 rather than y the real observations, and we'll try and reduce the number of subscripts. And so in this particular case, then, the likelihood function is just simply the product of the likelihoods for the individual units, and the prior is dependent on the hyperparameter, and then these are all the parameters. And simply because of conditional independence, then the posterior distribution will factorize, and so you've got if you like, the posterior distribution of alpha given x multiplied by the product of all these. And so if we look at a particular locus or particular unit, then we have the joint posterior density here, okay, which means that we could think of dividing the problem into two sorts of problems, so that we could have symmetric summary statistics that just depend on all the loci together, and then unit-specific summary statistics that depend on are just measured from a particular locus, for example. And we devised, there are a number of different algorithms that you can work on, but we devised a particular algorithm to look at this sort of problem, which is an approximation. And I'll talk about the approximation in just a minute or so. But the essential idea is that we use the ABC method to get the posterior distribution of alpha, and then we resample from this alpha that we've obtained empirically. So it's quite similar to a sequential algorithm. And we then simulate the sample of observations for each locus. And the reason for doing this is that it means that it's much more efficient in terms of storage. And so we break the problem down into two bits. We can automatically, using our symmetric summary statistics, we get the posterior distribution of all the hyperparameters. And then we can get posterior distributions for the individual units by following this algorithm. And unfortunately, this algorithm involves an approximation, and I'll just quickly skip through these slides. Essentially, we obtain a sample from this distribution, okay, which is not the target we want. The target we want could be obtained by just having a very slight modification where we compute the posterior distribution of the alphas based only on all the data minus the data corresponding to the locus that we're interested in. And if you do that, then you can show that you end up with the correct posterior distribution. And so the difference between these two algorithms is essentially that we would obtain the correct distribution if we just didn't use the data that in the calculation of alpha that we were interested in at that time. And the assumption is that the posterior distribution of alphas, if there are a large number of units, large number of loci, is going to be relatively independent, okay, of these is going to be relatively independent of these particular data. Okay, so I'll just quickly whiz. We have a very quick, very complicated model, but what we're interested in is trying to estimate selection. And the method works quite well. So up here is the posterior distribution that a locus is under selection according to our criteria. We've simulated 100 loci, 95 of which are neutral and 5 of which are under selection. And these are the posterior distributions that we get. And you can show that the method, this ABC method, is competitive with the full likelihood method and exceeds it when the assumptions of the full likelihood method are vitiated. And here's an application to some chimpanzee data, and I'll just very briefly say that, ironically, this approach may not have a strong future in population genetics because there are many other sort of competitive approaches. But one area that's quite interesting to me, and it's a project that I'm involved with, is using it for agent-based modeling. I don't know if anyone came across the recent Nature papers, but there's an interest in this in economic modeling, and these authors just point out that we need to, there's a huge problem in trying to fit parameters in these models. Okay, I'll stop there. Sorry for overrunning.
Normally when you see a title which is 3 lines long, you think that the person who actually wrote the title didn't actually know what they were going to talk about when they wrote the title. And there may be some truth in that. But actually, I mean, I did really want to, in this talk, when Christoph wanted me to talk about future directions of Bayesian computation, I did want to sort of bring in various different areas which I thought were sort of important. I work in inference for stochastic processes. I also work in sort of algorithms and MCMC algorithms, important sampling, perfect simulation, these kind of things. And I was sort of looking for kind of common themes that go through them, and latent variables was something that was is something that seems to come up an awful lot, and it resonates a lot with Mark's talk very much. That you know, one of the sort of future challenges is that many problems at the moment are ones in which likelihoods are not completely specified or not easy enough to write down. My motivations are different from those of Mark, but I think the sort of a lot of the similar themes are actually coming up. So this is the sort of roughly what I'd like to talk about. I'm not quite sure I'm going to be able to get through all of this, but I'd like to, if possible, get on to the 4th topic because Mark said I would talk about it, so I like to keep my promises and get to that at least. Since that work was very much inspired by previous work by Mark as well, and so I'd like to be able to say something about that. I'd like to start off with an introduction, which is something to do with basically my motivation, the kind of problems that I work on, and why I'm sort of formulating problems in the way I am. Sections 2 and 3 are really quite related, and they're all to do with work I've done on diffusions, simulation, and inference, in particular for diffusions. And I'll try and sort of give as much of detail of that as I can to make it sort of coherent. Throughout, I'll try and give some examples. Examples I'll give will all be simple. I don't want to be basically describing complicated models and things which might get in the way of this sort of simple picture I'm trying to sort of get across. So these are some of my motivations. Many of the problems that I look at really come from high-dimensional simulation, or actually, in principle, infinite-dimensional simulation problems. For instance, I'm just going to give a couple of examples here, and one of them I'm going to talk about a lot more later, is if you look at diffusion processes. Mark, could I borrow your pointer?
It's running out of battery, but
Right, thank you.
it's okay for a bit.
Okay, thank you. Okay, so diffusion processes are such processes given by, thank you very much, Mark, given by the equation at the top here. If you're not familiar with diffusions, then they're very, very natural statistical objects which basically have this kind of structure that you can see that the increment in a small time period is just given by alpha times dt plus an increment, a small increment of Brownian motion. So statistically they make an awful lot of sense, and in particular a very natural way of actually simulating them is to write down sometimes called the Euler-Maruyama approximation, or the completely obvious approximation to most people, which is just to say that an increment in a small time period should be Gaussian with the appropriate mean and the appropriate variance. Okay, so that's essentially based on a discretization of the stochastic differential equation up at the top. So this is intrinsically an infinite dimensional problem, because actually if you want to simulate the diffusion at all time points, perhaps on 0, 1, then there are infinite number of time points that you need in order to actually have all the information about the trajectory of that diffusion. Okay, so the trouble is though that you may not be interested, for whatever purposes, statistical or Monte Carlo or just as a pure simulation, you may not be interested actually in all of that diffusion sample path. You might be just interested in some of it. But if you look at things like this sequential simulation method here, the trouble is if you want to get at x evaluated at time 1, say, this is something that's going to be very difficult to do without basically simulating many steps of this. So there are two problems with this. The one is that this is an approximation, except in very, very special cases, this is an approximation no matter how small delta is. And the second one is that actually it's computationally very expensive, because to make it a reasonable approximation, you need to make delta smaller. Okay? And of course, there are better approximations that you might use, but they're still approximations, and they turn out to be more expensive to apply. So I'm interested in methods in which we can do simulation for objects such as X in this context, and to do Monte Carlo kind of things, in particular related by inference problems related to diffusions of this kind. But I'd like to be able to avoid having to use cumbersome approximations such as this, which I don't know much about and I can't quantify errors for. Especially if I'm doing Bayesian computation, I think it's particularly important. Okay, just to give another example, which I won't talk about, but it's just a very, very different type of example. If I look at a Dirichlet process, which can be represented as an infinite sum of point masses at various values AI, so this is a Dirichlet process is a random probability measure. That random probability measure requires essentially an infinite amount of random variables to be simulated in order for you to write down X. So you can't, in principle, you can't at all write down what the Dirichlet process value actually is. But you may still want to use the Dirichlet process in various problems. For in particular, you might want to be using it in Bayesian nonparametrics or various other areas. Okay, so this is another situation in which we might be interested in finding some way in which we can get representations of these infinite dimensional objects in a way which isn't infinite dimensional. Okay, so now I'm going to give a very, very abstract problem and hopefully sort of make this more concrete than when we talk about a specific example. So this is my random variable now, X. It could be the Dirichlet process. In our examples, it's going to be the sample path of a diffusion process. In particular, I'm going to assume that it's high dimensional or infinite dimensional random variable. Okay, it's got probability measure P. In principle, I could simulate it by some kind of approximation method. But actually, I'd like to simulate just some finite amount of information. For instance, for the diffusion, I might be interested in simulating X at time 1, or X at time 1 and X at time 2. Okay, so that's number 1 on my wish list. I'd like to be able to do this. Number 2 is basically to say, well, I'd like to have some mechanism for essentially simulating, once I've simulated h of x, for recovering further values of the process. So I'd like to be able to recover, say, g of x, where g talks about the values of x at time maybe half and 1.5. Okay, so I might be interested in the distribution of x at time half and x at time 1.5, conditional on x at time 0, 1, and 2, or something of that kind. Okay, and this is typically a difficult problem, even mathematically, to write down distribution of conditional diffusions is actually quite a messy thing to do. Okay, so that's something we might want to do. If this is too difficult, we may well want to produce some kind of robust and efficient unbiased approximation estimation for some expectations of this. So we want some way of doing this in an unbiased way. Okay, so the traditional way of doing this kind of problem is to basically look at finite dimensional approximations, such as the Euler-Maruyama approximation, and to work with that. But of course, this has a problem of the uneasy balance between computational cost and accuracy. Okay, so the very simple idea is that latent variables can be very powerful for us in this kind of context. So let's introduce, we've already got this infinite dimensional object x, and I'm also going to introduce y, an auxiliary variable, in which what I'd like to be able to do is simulate some finite dimensional representation of x and y together. Now, y itself may be very simple. It needn't. I don't want to specify anything about it. But what I'm going to do is I'm going to suppose that maybe I can actually simulate x and y together, and it will give me h of x, k of y, or some joint functional of x and y. And you won't believe it from this because we need to look at examples, but it turns out that if I do this in the right way, this recovery strategy of actually simulating further functionals of x, conditional also on the latent variables, is something that's often considerably easier if you do it in the right way. So basically, if we choose the right kind of structure for the latent variables, then magical things can happen for the conditionals, which allow us to then sort of do computation much, much easier. And the example which I'm going to look at some detail, which is in filtering for diffusions, is something in which it turns out to be most efficient to do unbiased Monte Carlo, even though we could do simulation instead. So, okay, so I'm just going to go through some very simple examples. I'm sure you all know these, but just to sort of talk about latent variables to sort of remind you that in your mindset you're using latent variables all the time. People don't look at this density anymore without sort of subconsciously thinking this is a mixture of two normals. And so you're thinking that there is a latent variable in there that takes the value 0 or 1, depending on what the mean is. And that's automatic, and statisticians think in this way. So that's a natural situation in which a latent variable is something that we'd automatically put in. Something that's a bit less automatic is if we go back to the sort of algorithm point of view. If we look at rejection sampling, which is one of the first algorithms we teach in our sort of master's computational statistics course, then we're using auxiliary random variables, uniform random variables, to decide whether or not to accept your proposed value. Well, actually, it turns out to be useful and sometimes very, very, very profitable, not just to think of that as some kind of Monte Carlo nuisance that we actually have to use, but to actually think of it as a latent variable, to think of it as something that we can explicitly put within the model. Okay? And this resonates with the very nice ideas of slice sampling that various people have worked on in recent years. Okay, so we use these things a lot of the time without even knowing that we're doing it. The old ideas, I first came across auxiliary variables and statistics in Bizak and Green's paper, but certainly older than this. And then these are the sort of most sort of trivial things you can say about it, that if you can simulate from this x together with a latent variable y, then we can certainly simulate from x. We can, the worst comes to the worst, what we can do is we can just throw away the values of y and we're left with x. Okay, that's a trite observation, but it's useful. The other thing is that very often we can do better, because if you can actually compute explicit expectations conditioned on the latent variable, and in many of the models I'm going to talk about you can do, it turns out that this z, of course it's an unbiased estimator, in the same way that x is, and it has a smaller mean square error. Okay, so trivial observations and things which actually give us quite substantial potential advantages in Monte Carlo. Just to sort of, so some people sometimes wonder about why unbiasedness is a sort of useful thing. I mean, obviously in traditional statistics we drum into our students quite early on that actually unbiasedness is actually not particularly important as a property in many statistical contexts. But of course in Monte Carlo, data is in some sense usually cheap. If you can actually simulate 1,000 samples, you can probably do 2,000 as well, and you can always get more data. And unbiasedness is clearly needed for consistency. So in some sense, unbiasedness is a hugely more important property in Monte Carlo and in Monte Carlo inference than it is as a statistical property within statistics where you've got to have a fixed data set. Okay, so I'd like to now talk about a sort of an example of this, which is to talk about exact simulation of diffusions. So the idea here would be that we have this diffusion where I'm just going to look at the simplest possible case here where I have a diffusion which has a drift coefficient alpha and a diffusion coefficient which is just a constant. Okay? And I'm going to assume that the diffusion is just one-dimensional. And I'm going to introduce a few things here, so I'll try and go over this relatively slowly, but I'm going to introduce two other probability measures. Well, the natural one to think about is that suppose I didn't have an alpha in here. Then all I'd have left would be this Brownian motion. Brownian motion is something that we understand well. We can simulate from Brownian motion. It has a multivariate Gaussian distribution, so we can work with Brownian motion without any problem. But that's not what we want to work with. We want to work with something else, and what we use is something called biased Brownian motion. And biased Brownian motion shares a property with Brownian motion in that it is something that we can simulate exactly without approximation, but is actually biased in the sense that what I do is I perturb the distribution at the terminal point, time 1, which I've chosen it to be here. So what do I mean by this? I mean that if I look at the probabilities under Q divided by the probabilities for Brownian motion, if I look at a trajectory and I look at the ratio of those two probabilities, then essentially that's equal to the exponential of capital A of x1. It's just a function of the terminal value. What is capital A? Capital A is just a function given by the integral, the ordinary deterministic integral of the drift function alpha. I'm sorry, Mark, I've run out of battery completely now. But, so now we're in the situation that we have a biased Brownian motion which...
There should be a handheld pointer there.
Oh, thank you. Yeah, this thing here. Yeah, I think.
With the middle button.
Thank you. Okay. Okay, so we've introduced this biased Brownian motion. It's a bit of a weird thing, but battery's going on this too. It's a bit of a weird thing because it looks a little bit like Brownian motion, but it differs only in the terminal point. So the way the key to simulating from biased Brownian motion is that you can simulate the value at time 1, which is no longer a Gaussian random variable, but it's a perturbed Gaussian random variable. And then condition on that, all the conditional probabilities are the same as if it was a Brownian motion, in this case a Brownian bridge. So biased Brownian motion can be simulated, and it's a nice thing to work with. And it turns out that we can write the ratio of the probabilities between the diffusion of interest and this biased Brownian motion by this formula here at the bottom here. And this formula here turns out to be rather nice because it's just essentially a Lebesgue integral as a path integral of the process X. Okay. Now, again, there are some concepts in there which, some functions in there which I don't want to go through in too much detail, but the function phi is a function which is just derived from alpha, the drift of a diffusion, and it's just given by alpha squared plus alpha prime over 2. And the minimum value of phi is given by this curly L. Okay. Okay, this is just completely sort of elementary stochastic calculus to be able to write this down. But the whole point about this is that when this is essentially like a ratio of densities, this expression here, and when we're in that context, it's natural to think of being able to do simulation or importance sampling by rejection sampling or importance sampling. And that's exactly what we're going to try and do. But the problem is that normally in rejection sampling, one thinks of having to actually compute this integral here, this integral on the right-hand side. We want to actually compute the ratio of the two densities. If we were to compute that, we'd need to know the value of x at all points and therefore and then calculate that. So that's something that would require an approximation, and we can't use it. But then there's sort of a nice sort of trick that gets us round this, which is nice. But this is where latent variables turn out to be crucial. And so we introduce something called, well, it's just a Poisson process. Call it V on the infinite strip 0, 1 cross 0, infinity. Okay, so 0, 1 is our time, and 0, infinity is essentially the sort of values in the state space. And essentially, if I now look at this event S, which is, it's essentially a product of indicator functions. It's something that's going to take the value 0 or 1. It's going to be 0 unless all those events are true, and it's going to be 1 if that event is false, if any of those events are false. Okay, so there's an event A which involves each of the yi's, which are the yi's are the height values for the Poisson process points. If they all exceed phi, which is the function we introduced on the previous slide, are evaluated at the process x minus its minimum value. Okay. Now, we don't need to go through the calculation, but it turns out if you integrate out v from this expression, okay, you take an expectation with respect to v, it turns out to be exactly equal to that ratio of densities, which is exactly the thing we need for the accept-reject probability. Okay. So by using the Poisson process, I found a way of actually computing an event. I've basically found, so the expected value of S is something that is a probability. It's going to be 1 with a certain probability. The probability of A, it's going to be 0 otherwise. But the probability of that event A is exactly the probability I need for my rejection sampling algorithm. Okay. The only trouble is to actually compute S is actually then given by an infinite product. And again, an infinite product needs you to be able to evaluate the process X at all the time points of this Poisson process. And this Poisson process typically will have an infinite number of points. Okay, so that's something which we want to be able to avoid. But just thinking about it sort of in an abstract way to start off with, so if you can just think of it as a sort of factorization. If V is the distribution of this unit rate Poisson process, and Q is the distribution of biased Brownian motion, I put them together and make them independent. And if I then just condition on A, this fancy event A, which is quite complicated, but at least I can write it down explicitly, then the first component to that is just basically the law of a diffusion. That's the P that we're interested in. So that's something which is just really a sort of a fancy mathematical statement of rejection sampling in some sense. But it is something that allows us to potentially sort of use this in practice. But how are we going to do that when S is something which needs to be addressed? So in order to know whether to accept or reject, going back to the S formula for S up there, in order to be able to accept or reject, we need to be able to evaluate that infinite product to see if all those events are actually true. Okay. And I think all I'm going to have time for probably today is to, maybe I'll very briefly, but this is the simplest case is where phi is actually bounded above. This function phi, if that function phi is bounded above, then it turns out that actually the only points in this infinite Poisson process that really matter, for which there's a chance that actually the condition may be violated, are points in the rectangle 0, 1 cross 0R. So in other words, we can actually replace that infinite product by that expression for S that we actually have at the bottom of the screen there. And this is an algorithm which we call EA1. And I think I'm just going to show you this via a diagram. Okay, so this is a diagram which shows EA1 in action. What's this really doing? How I implement this algorithm is I first of all simulate a collection of points in that unit rectangle there, and you can see that's all the x's in there. There's currently 5 points. Okay, right. In order to accept this Brownian, this biased Brownian motion path, what I need to do is I need to basically evaluate this function phi, evaluated at each of the data points for the time values of that Poisson process. So in other words, I need to evaluate the blue dots there. It's not very clear there, but there is a sort of jagged diffusion-y-like function that leads between the blue points. If all the x's are above all the blue points, then I can accept the whole path and everything's finished. If any of the x's are below the blue points, then I reject and I carry on as rejection sampling would do. And this is going to be exact. There's no approximation here. But the problem is that potentially that this doesn't really give me any information apart from the values of the process evaluated at those time points. There, those 5 time points I've just written down there. Okay, let's go to this. So this is exactly what the algorithm gives. The algorithm outputs red dots like that. They're randomly chosen points. The distribution of the times at which you know the diffusion. It's rather subtle. It was Poisson, but now it's been affected by the conditioning event, so it's not quite Poisson anymore. But then one of the crucial things is this retrieving property that we wanted to have is something that we can do very easily here. And the reason we can do it very easily here is because we were, in principle, for our proposal distribution, simulating from a biased Brownian motion, and a biased Brownian motion can be simulated from those red dots very easily just by interpolating by Brownian bridge interpolation. And the point is that any such paths in between the red dots don't have any effect whatsoever on the accept-reject decision. The accept-reject decision and any of the rest of the sample path are conditionally independent, conditional on the skeleton, the red points that we've actually simulated. So we can always go back and simulate any further dots in that sample path that we want to without having to sort of worry any further about any complex calculations, just by basically calculating a normal random variable. Okay, so I want to sort of very quickly go through this just to say that in the situation where this function phi is not bounded above, then we have various problems. And one of the problems is that in principle, we could still have many other points in that infinite Poisson process which could affect the accept-reject decision. And the way that we have of dealing with this is a way to simulate from a modification of the, well, it's still biased Brownian motion, but we simulate also additional information to do with its maximum, related to its maximum and minimum values. In fact, we basically split the whole region into kind of strips, and we basically judge things based on which strip you can get to. Right, so I'd like to talk more about that, but I think I'd better not. Okay. Okay, so that's a pure simulation algorithm. Now, so what I'd like to go on to do, because we use that in many situations, so with Omeros Papaspiliopoulos and Alex Beskos and Paul Fernhead, we have a paper in RSSB a couple of years ago in which we do maximum likelihood estimation and Bayesian inference using the kind of methods directly that I've just been talking about. But I'd like to talk about some somewhat more recent work which is all to do with using this methodology in filtering. But I'm not going to use the methodology in exactly the way I described, because it turns out that important sampling methods, which are based on exactly the same ideas, turn out to be slightly more efficient. Okay, so this is the sort of the general situation I'd like to talk about. I have a diffusion, x, which is given by the stochastic differential equation at the top here. This is just the gradient of some general function a, and again I'm assuming a unit diffusion coefficient, which is a real assumption and a serious assumption, not always holding. One nice thing about diffusions is that at least you can have mathematical expressions for the transition density. This is a very useful one for us, which is the transition density can be written down in terms of things that we know and things that we don't know. The things that we know are, well, this is just some kind of normal density. This is the exponentials related to this function a that we know from, because it's part of the definition of the diffusion. And finally, this term at the end is an expectation of minus the integral of phi, which is a function which is essentially the multivariate version of the phi function we had earlier, which is given by this expression in terms of a. Okay. So this is very similar to what we did with the rejection sampling perfect simulation approach. In that approach, essentially what we did was we said, well, this expression on the right-hand side here is an expression that we can actually simulate from an event of that probability. We're going to do something slightly different, but very, very closely related here. Okay. So the trouble is you don't have the transition density. So there's standard methods for doing filtering in discrete time when you actually know the transitions of the process are things which can't be directly applied. Okay. So the sort of things we've looked at, and don't worry, I won't be showing all of these, are these kind of observation regimes. So it's quite sort of flexible. The most obvious one, and it's probably the only one I'll look at, is diffusions observed with error. Okay, but also you could have situations where you observe perhaps a one-dimensional component of a two-dimensional diffusion or something of that type. Cox processes where actually you have a latent diffusion process which determines the rate of some kind of events that you observe at particular times. And the fourth one is an interesting one where observations are in principle available continuously, although accessing them continuously is something that would be prohibitively expensive. And actually it turns out that what we do here can actually give a very natural way of deciding exactly the timescale with which to actually access the data without losing information. Okay, so I'm not going to talk about probably B, C, or D. Okay, so here's a very simple example. It's a sine diffusion. We have drift, which is sine x dt, and plus dbt, and we have Gaussian observations based around it. Okay, so this is a diffusion which is obviously a toy example, but it does have some sort of interesting sort of metastable kind of behavior. And I'm going to be using standard auxiliary particle filter approaches in which I want to be able to update weights of my particles representing the filter distribution, essentially by accessing expressions such as the equation there. But the trouble with that is that it's not available, the transition density of a diffusion, and therefore we need to basically estimate the transition density, this pxi plus 1 given xi. Okay, so this expression here, how are we going to do this? And so what I'm going to talk about now is very briefly is that how can we get unbiased estimates of this expression in an efficient way? This is a sort of simple idea of how you do this thing. How would you estimate an integral between 0 and t of some function? Well, you can evaluate the function wherever you like, but you can't evaluate it everywhere because that's too expensive. But I want an estimate of that. How would we do this? Well, the obvious thing to do is to evaluate it at some random uniform time. Okay, and basically at that random uniform time multiplied by t and basically that would be an unbiased estimator. Okay, it doesn't matter whether f is random or not random. This gives an unbiased estimator. Okay, we can make it better by having multiple observations if we want, but we can certainly just do that. If we want to estimate I to the k, an unbiased estimator can be obtained just by looking at a number of different, well, 2 in this diagram here, values. So all I need to do is evaluate f at 2 different values. Okay. So if actually the f itself is a trajectory of a diffusion, I have to do this by doing some kind of conditional simulation, because the joint distribution of those 2 red points, well, they're certainly not independent, so I can't just do them independently. Okay. So what we do in what we call the generalized Poisson estimator is, first of all, we want to estimate the expression on the left-hand side at the top, and we're going to do a Taylor series expansion of the expression giving powers, and once I have powers, I can then use the methods I was just been talking about. So just cutting to one, I think, sort of an important issue that comes up here is that the estimates that we obtain for the weights in the particle filter in this context turn out to be potentially negative. And even though they're unbiased, the weights themselves are potentially negative. And this is obviously undesirable if you want to interpret the current particle filter as some representation of the current distribution. And it turns out that we can actually get a method to ensure, on the basis of an arbitrary estimator, that we have positive estimators always. And that's in a recent paper with, again, with Omeros, with Paul Fernhead, and with Andrew Stewart. So this is very much ongoing work and things that we've been working on quite a lot recently. Well, with apologies to Mark for not saying anything at all about what I wanted to about his talk, I just wanted to just conclude and sort of say, well, I think that I think this motivation for this work continues to grow. There's more and more areas in which it turns out that this is a kind of crucial issue, basically unavailabilities of likelihoods. There's this very interesting duality between a sort of passive Monte Carlo, well, we actually have to do it anyway, so just let's approximate as well as we can, and auxiliary variable methods, which can often actually, in my opinion, actually be sort of, it's advantageous to be using sort of extra randomness because it gives you extra tractability in other ways. And I think there's many new exciting challenges in this area, especially in inference for stochastic.